We've all had software crash on us. It's annoying, right? But what if a reboot just wasn't an option? What if Control-Alt-Delete was millions of miles away? Today, we're going to dive into the world of code that absolutely, positively cannot fail. We're talking about the software that flies spacecrafts and navigates rovers on Mars, where the cost of a single bug isn't just an error message, it's a mission-ending catastrophe. So that's the real question, isn't it? When you can't just turn it off and on again, when one tiny mistake can vaporize hundreds of millions of dollars in a decade of work, well, you need more than just good coding habits. You need an ironclad philosophy. So how on earth, or off it, does NASA actually do it? Well, the answer comes from NASA's Jet Propulsion Laboratory, JPL. And what they did was they distilled decades of really hard-won experience into just 10 rules. But listen, this isn't just some simple checklist. This is a disciplined philosophy. It's designed to make software so straightforward that it can be formally proven to be correct. And when you look closely, these 10 rules, they aren't random. They actually cluster around 3 powerful core principles. Okay, so that first principle is all about one thing: forging clarity. The goal here is to eliminate every shadow, every single dark corner where a bug could possibly hide. The logic has to be so ridiculously straightforward that it's completely transparent, not just to human engineers, but also to the automated tools that have to verify it. So, rule number 1 goes right on the attack. It targets complexity at its source, the code's flow. It completely bans things like go-to statements, which can create these tangled, unpredictable paths. And it also bans recursion, which can just eat up memory in really surprising ways. The whole point is to force the code down a clean, linear, and easily predictable highway. And here's the real genius behind that decision. By banning recursion, you are guaranteeing that the function call graph is acyclic, which is really just a fancy way of saying no function can ever get stuck calling itself in a loop. And this is critical. It allows engineers to mathematically prove that a program will finish on time, and, maybe most importantly, to calculate its exact memory footprint before it ever leaves Earth. Look at this comparison. The go-to approach? That's what developers call spaghetti code. I mean, if you need to add another resource, you have to remember to patch in the cleanup code in multiple places. That's a recipe for human error. The structured approach, on the other side though, it's clean. Each resource is handled in its own block, which makes cleanup localized, logical, and way, way less likely to fail. Next up, Rule 4 enforces that clarity through constraint. It says functions must be short, and we're talking typically under 60 lines. Now, this isn't just about being neat, it's what's called a forcing function. It literally compels developers to break down problems so that each function does one single logical thing. And a function that does only one thing is a function you can easily test, verify, and ultimately trust. Just think about trying to test this. The original big function on the left is a total black box. Data goes in, something magical happens, and then data comes out. It's an absolute nightmare to debug. But after refactoring, what you have are 4 distinct testable units. Each one is simple. And now the main function reads less like code and more like a clear, high-level summary of the entire process. It's basically self-documenting. And this whole philosophy of clarity, it just ripples through other rules. Rule 6, for instance, keeping variables in the smallest possible scope prevents them from being accidentally changed somewhere else in the code. And Rule 8, that one tames the C preprocessor, which is a really powerful tool that can easily hide complex logic and fool even the sharpest developers. Every single one of these rules is designed to drag potential bugs out into the light. But, clear code isn't enough if it's not also predictable. And this brings us to the second principle: guaranteeing predictability. Out in deep space, you have finite resources, time and memory. And you have to know with 100% certainty that your software will never, ever overspend its budget. Rule 2 is a cornerstone of this predictability. It dictates that every single loop, no exceptions, must have a statically provable upper bound. This, combined with that ban on recursion we saw earlier, makes what's called runaway code completely impossible. It is the key to proving that a critical task will always finish and meet its non-negotiable real-time deadlines. I mean, here's a perfect example. A standard loop might just traverse a linked list. But what if a single bit flips because of some cosmic radiation and it creates a circular link? Well, that loop now runs forever, crashing the system. The JPL-compliant code, though, is immune to that. It adds a simple safety counter. So no matter what happens to the data, that loop will stop. making the code robust against the harsh realities of space. All right, this next rule, it might sound extreme, but it single-handedly eliminates an entire class of the most insidious software bugs out there. Rule 3 forbids dynamic memory allocation, so using functions like malloc after the system has initialized. All the memory you need has to be claimed right up front. And yeah, it seems restrictive, but it's a direct counterattack against a very specific enemy. And that enemy is called memory fragmentation. Just imagine your available memory is a single solid block. Now, as you allocate and free chunks of different sizes over a long mission, that block gets chopped up into smaller and smaller pieces. Eventually, you might have enough total memory free, but it's all in these tiny, useless fragments, so you can't allocate the one large block you actually need. Rule 3 just makes this entire problem impossible by design. So instead of the unpredictable malloc, which can have random timing and all sorts of failure modes, the code uses a simple pre-allocated static array, a memory pool. Allocating from this pool just means taking the next available slot. It's super fast, it's deterministic, and the system's total memory footprint is known and verified before the rocket ever dreams of leaving the launch pad. Okay, so this brings us to our final principle. Creating clear and predictable code is the start. But the JPL philosophy demands that correctness be proven, not just assumed. And this is all about verifying everything through a deeply defensive mindset. Rule 5 mandates the heavy use of assertions. Now, an assertion is just a simple check for a condition that the programmer believes must be true. Think of it as a form of executable documentation. If an assertion ever fails, it's not a user error. It's a critical bug in the logic, and it stops the program right there. JPL actually demands an average of at least 2 of these per function. And this really shows the difference between blind trust and a robust contract. Without assertions, a function just kind of hopes its inputs are valid. But the robust version, it uses assertions to enforce a contract. It checks its inputs, the preconditions, before it acts, and then it verifies its own work, the postcondition, before it returns a result. This catches bugs the very instant they happen. This defensive mindset just permeates the other rules too. Rule 7 insists you check the return value of every single function because ignoring error codes is one of the most common ways bugs creep into a system. And Rule 9 restricts the use of pointers, which are a notoriously tricky feature of C, to make the code's data flow much easier for analysis tools to track and verify. And now the final rule. This one ties the entire process together with an absolutely uncompromising standard. All code must be compiled with the most aggressive warning levels turned on, and it must compile with 0 warnings. No exceptions, period. This quote right here just captures the intense discipline that's required. Modern compilers are incredibly powerful static analysis tools. They can spot subtle potential bugs that a human being might miss for years. By treating every single warning as a critical error, JPL leverages the compiler as a free, automated, and relentlessly picky code reviewer, which forces a culture of extreme precision. So after all of this, what's the ultimate lesson from NASA's code? Well, these 10 rules, they represent a fundamental trade-off. They intentionally sacrifice some developer convenience and a few powerful language features in exchange for something far more valuable: absolute, verifiable reliability. It's a philosophy of prevention over cure. So let's bring it all together, shall we? The first set of rules forges clarity, making code transparent and simple. The next set guarantees predictability, taming time and memory. And the final set verifies everything, building a defensive wall against error. Together, they create a system not just for writing code, but for proving that it's correct. While most of us aren't writing code for Mars rovers, these principles are universal. They teach us to value simplicity, predictability, and defensiveness. They show us how to eliminate entire classes of bugs by design, not just by chance. So the real question is, which piece of this rocket science are you going to apply to your own work?